Today we are going to look at the air standard cycles in thermodynamics. Just we have already seen what are the cycles. So how the cycles will look like. So cycle is a routine process. So it's the starting state and the end state will be the same, but there is some paths followed to achieve this same points. Then we can call that as a cycle. So we have lots of cycles as we are Russian working medium, so we are going to look at that. So in the last class itself we've seen what is Carnot cycle. So the Carnot cycle was introduced as the most efficient heat engine that operates between the two fixed temperatures, like high temperature and low temperature. The thermal efficiency can be calculated by the formula for Carnot. The thermal efficiency Carnot will be equal to 1 minus TL by TH. So this formula we seen in the last class. So right, so this formula we seen in the last class. Then upon derivations, the performance of the real cycle is often measured in terms of its thermal efficiency. So thermal efficiency also can be calculated by this Carnot cycle is compared with the other thermal efficiency of the cycles. So the thermal efficiency, you know the formula, W net by Qn. So output by input will be the efficiency. So thermal efficiency for any other cycles can be calculated with the use of this formula, that is W net by Qn. Right. So this is the however, the thermal heat transfer is difficult to obtain in reality. So but in reality we can't get the thermal isothermal heat transfer. So it requires large heat exchangers and a lot of time. Therefore, so this actually this Carnot cycle. So Carnot cycle will be a example of this one. Isothermal heat transfer will be happen in the Carnot cycle. Therefore, the very important Carnot cycle composed of two reversible isothermal process and a two reversible adiabatic process that you know already is never realized as a practical matter. So what we seen in the last class, that is not really practicable. So it is its real value is as a standard of a comparison of all other cycles. So we can take this as a standard to compare all other cycles. So we have a lot of cycles, thermodynamic cycles available. So we can have the standard of this Carnot cycle to any other cycles. So you know this is for your recap. So Carnot cycle will have these four processes, these four paths. The first processes will be reversible isothermal heat addition at high temperature, you know very well. And the second process will be reversible adiabatic expansion from high temperature to low temperature. Then reversible isothermal heat rejection at low temperature. Then reversible adiabatic compression from low temperature to high temperature. So this is the processes of Carnot cycles. Yes, you know. So I think this figure also you may seen. So first process, so high temperature isothermal heat addition. Then the reversible adiabatic process from low temperature to expansion, right? So expansion will happen. Adiabatic expansion will happen. So high temperature to low temperature will be there, right? Then the third process, you know, this one. So reversible isothermal heat rejection also. So here also there will be isothermal, there will be heat rejection. Then again reversible adiabatic process. So these four processes will give you a Carnot cycle. This is for piston cylinder arrangement. So just keep the processes in mind. So for Carnot cycles we have these four processes. So we have the PV diagram and TS diagram here. So you know, so first point is here. So isothermal here, isothermal heat addition, then isentropic, that is reversible adiabatic process, then again isentropic process, the isothermal process, isothermal heat rejection. Then there will be a reversible adiabatic process, that is isentropic process. So this is the PV diagram. Then also we have the TS diagram for the same. So, TS is entropy. So in this process, for isentropic process, there is entropy is constant, right? So we have 2 to 3 and 1 to 4 to 1 will be a straight line with respect to entropy. Also, we have isothermal process, so temperature lines. So temperature from 1 to 2, path of 1 to 2 and 3 to 4 is an isotherm. So we have a horizontal line with respect to the temperature axis. Right. So this is the PV diagram. So we can have the saturation lines. So this is a saturation liquid line. Then this is a saturation vapor line. Right. So this will the PV diagram and TS diagram will be look like this. Right. So each and every cycles will have the PV and TS diagram. So just try to draw. Then this is for your review. So we know how the ideal gas equation is defined. So don't get confused. If P and V in capital letter, there will be M R T. M is mass, then R is gas constant, then T is temperature. If V in small letter, that is specific velocity, specific volume. So we can get small v by M, right? So small v equal to capital V divided by mass, right? So in your assessment, none of write this exam this equation correctly. So just try to understand, if there is capital P and a capital V, there should MRT. So if there is small v, this V by M will we can write V by M as V. So this M will come this side, right? So if M will come this side, so we can get small v. So PV is equal to RT. Also equation for ideal gas equation. So if capital P into capital V will give you M into R into T. So if both the pressure and volume in capital, we have to use mass in the right hand side. If there is a small v, that is a specific volume, we can forget this mass, right? So just remember that. So this is the base for all the thermodynamics. Just try to understand this. So we have ideal gas equation. P is a pressure, then V is a volume. If small v is a specific volume, then we have ideal gas constant. Just try to remember the ideal gas constant as a number. Then we have mass, then temperature. So also we have a change in internal energy and change in entropy, enthalpy. So this is the internal energy. U is internal energy, specific internal energy. This is entropy. Sorry, enthalpy. So we have U2 minus U1 will give you delta U. Then that can be also written as CV T2 minus T1, that is constant specific heat capacity constant volume into change in temperature. Then we can have a change in enthalpy, that is H2 minus H1 is equal to specific heat capacity at constant pressure into change in temperature. So this is for your recap. Then also these slides will recap your processes. So we have a polytropic process. The equation will be PV power n is equal to constant. So here V is capital V, so volume. So PV power n will be a constant for all the processes. So that is for polytropic process. So we have lots of process like isobaric, and isothermal. So isothermal in the sense constant temperature, isobaric in the sense constant pressure, then isobaric constant volume. So also we have results of ideal gas laws. That is for isobaric process, we have these kinds of equation. Then for isobaric, that is V1 by Vt is equal to T1 by T2. Then for isothermal, we have PV is equal to constant. So we can have P1 V1 is equal to P2 V2. Then for polytropic process, the equation will be look like this. So just try to remember this equation. So we can have this equation for isentropic processes. So for isentropic process and polytropic process, all the three variables will comes. So in all the other three processes, there is only two variables will come. So this problem, this formula is easy to understand us, but this is difficult to understand. So just try to recall the formula. Just P1 by P2 is equal to V2 by V1. So because PV power n is equal to constant, so P and V are in indirect proportion. So we have to write in this manner. So P1 by P2, if you want to take relationship between pressure and volume, we can take these two. Or if you want to take relationship between pressure and temperature, yes, we can take these two. Or if you want to take the relationship between volume and temperature, we can take these two. So if you take volume and temperature, this V2 by V1 power n is equal to T1 by T2 power n by n minus 1. Then this n can be cancelled. Then finally we can have V2 by V1 is equal to T1 by T2 power 1 by n minus 1. Right. So this we can understand by this way for all the processes. So this is for review. Then also we can review the constants. That is R is universal gas constant, ideal gas constants, that is 0.2871. Also this is available in your property tables and charts. Yes, you can take from that. Also this Cp is constant specific heat capacity at constant pressure, that is 1.005 kg per kilojoule per kg Kelvin. And we have specific heat capacity as constant volume, that is 0.718 kg per kilojoule per kg Kelvin. So for ideal gas, the K will be 1.4 or N will be 1.4. So this is the constant for ideal gas. So just try to remember these values. Also these values will be available in property charts, but rather to refer that, just you can remember these values. Then you know R is ideal gas constant, then Cp, then K. K is a specific heat ratio. And then come to the second unit. So we have IC engines. You know what is IC engines? That is, combustion of fuel takes place inside the engine's cylinders. So internal combustion engines can called as an IC engines. So there will be combustion inside the chamber, right? So these are the examples of IC engines. So this generator, these vehicles, all the automobiles will be working principle of IC engines. Just you can refer that. Then so these are the assumptions for air standard cycles. So we have to assume air is a continuously circulated in a closed loop. Just you have to assume air in the cycle is continuously circulated. Also always behaves as an ideal gas. So just we have to assume the air what we are using as a working medium, it should be an ideal gas. Then all the processes that make up the cycle are internally reversible. So we know what is reversible process. Then the combustion process is replaced by a heat addition process from an external source. So if the heat is added externally, yes, there will be a combustion process will happen. Just these are the assumptions. Then we know what is how the combustion chamber works. So if air fuel mixes will send to this combustion chamber, there will be a combustion process will happen. Then if air is passed through this heat section, then if heat is added, then we can get the combustion process also. So this, you know what is combustion, just try to recall. Then other assumptions are a heat rejection process that restores the working fluid to its initial state, replace the exhaust process. So right, so if after the combustion process there will be a again restoration restores of the working fluid. Right, again the position initial state will comes back. Then the cold air standard assumptions apply when the working fluid is air and has constant specific heat evaluated at room temperature. Just we have to assume the process is happening in the room temperature, that is 25 degrees Celsius or 77 degrees Fahrenheit. Then we have to assume there is no chemical reaction takes place in the engine. So these assumptions must be taken in, for understanding air standard cycles. Then these are the terminologies for reciprocating devices that we know. A piston cylinder arrangement is a reciprocating device. So we have to understand what are the terminologies used in the piston cylinder arrangement. So there will be a TDC and BDC. So DDC in the sense top dead center, and PDC in the sense bottom dead center. It is DDC in the top of the piston. Top of the cylinder, then BDC in the sense bottom of the cylinder. This is the volume, right? Then stroke in the sense from this TDC to BDC. This is called one stroke. Then bore is the volume of this cylinder. Then intake valve. So this will give you supply to the cylinder. Then there is exhaust valve, that is we can exhaust the combust air by the use of this exhaust valve. Then clearance volume. So beyond this TDC there will be some volumes. So this is for clearance purpose they provided. So this can be called as a clearance volume. Then there will be a displacement volume. So this TDC to BDC will call as a displacement volume. Then compression ratio and mean effective pressure that we can be seen in the next slides. So these are the terminologies. So we have a cylinder, we have a piston. So if the piston is in top, that is top dead center. If the piston is bottom, that can be called as a bottom dead center. So from DDC to PDC, we can call a stroke. Then bore is a volume of TDC to BDC. Then we can calculate the volume. We can assume the cylinder, right? So by the use of cylinder formula, we can calculate the bore. Then we have intake valve. Then we have exhaust valve. Then we have clearance volume. So this is the volume where we can work the air combustion, right? Then these are also terminologies. So we know bore, what is bore. Then we know what is stroke. We know what is the displacement volume. So displacement volume can be calculated by stroke into the volume of the cylinder, pi before d square. Then we can have the clearance volume that can be called as the CV. Then we have a compression ratio that is can be called as a small r ratio, compression ratio, that can be calculated by this formula dV plus CV, that is displacement volume plus clearance volume, the total volume of the cylinder divided by clearance volume of the cylinder. R can be called volume of BDC divided by volume of TDC. Right. So these are the terminologies in reciprocating devices. Then the compression ratios of an engine also the same formula, right? So R can be calculated by V max by V minimum. So that is V BDC divided by V TDC. So maximum volume of the cylinder can be V BDC, and the minimum volume of the cylinder can be V TDC. Then from that we can calculate the compression ratio R. Then we have the other terminology, mean effective pressure, that can be called as MEP. That is a fixtures process that if it operates on the piston during the entire power stroke would produce the same amount of net work. So for mean effective pressure, if you give us any power, that can be converted into entire net work. right? As that produces during the actual cycle can be calculated with the use of this formula. That is your mean effective pressure is equal to W net by R. That is sorry, W net by stroke. So V max minus V minimum. That also can be written as, these are the capital letters, so we can have W net by V max minus V net. Also we can have W, small w net divided by small v maximum minus small v minimum. Right, so from these equations we can also have the net work output of the cycle is equivalent to the product of the mean effective pressure and the displacement volume. So this V max minus V minimum will give you the displacement volume. Right, you know how to calculate the displacement volume. So this displacement volume into your mean effective pressure will give you the W net. So the net work output of the cycle is equivalent to the product of the mean effective pressure and the displacement volume. So we can rewrite the equation as like this. So W net is equal to displacement volume dV into MEP. Then this is the PV diagram of piston cylinder arrangement. So these are the processes. So this is so this is V minimum, volume minimum. So here, so this portion we have the minimum volume. Then all these portions will have the maximum volume from this to this maximum volume. So we can have maximum. Then so area under the curve, this curve can be work. The work done can be calculated by calculating the area under the curve. So if the piston cylinder is an actuator, then we can get this PV diagram. Then from this PV diagram we can calculate the work done. Then if you calculate the mean effective pressure, this will be in this range. Actually this is a pressure, so this will be less than these other pressure values, right? Then this is the Otto cycle, ideal cycle for spark ignition engines. So you know what is spark ignition. So this is a piston cylinder arrangement. The first stroke is compression stroke, then second stroke is power stroke, that is expansion stroke. Then third step is exhaust stroke, then fourth step is intake stroke. So in this compression stroke, the air inside the cylinder gets compressed. That is air fuel mixture in the cylinder is get compressed, but the valves are closed. Then in the expansion or power stroke, the compressed air get ignited by a spark plug. This spark plug. Then we can expansion by the air. Then the piston will comes to down. Then this is called expansion stroke. Then we have exhaust stroke. After comes down, the burned air will get exhausted by the use of exhaust valve. Then again there will be air fuel mixture will comes to replace the vacuated chamber. So the air gets filled into the cylinder. That can be called as an intake stroke. So if air gets intake, then we can call that an intake stroke. So there will be a intake, there will be exhaust, there will be a compression, and there will be a power stroke. So these four strokes will be important for spark ignition engines or IC engines. Then so this is the PV diagram actually. So exhaust stroke will be, so we can start from the compression stroke. So where is a compression stroke? So from this, the volume will be actually more, right? So at the start point, at the starting this point, so this point, the cylinder will be in BDC. So there will be a more volume. Then if this gets compressed, we can get this isotherm. Then the volume will get reduced. Then the piston will be in TDC, right? So will be directly to TDC. Then after compression stroke, we have expansion stroke. So here, if you initiate the spark plug, we can get combustion. Then this is the end of the combustion point. Then after combustion, we can get the expansion. So if the air fuel mixer inside the compressed chamber gets ignited, we can get the expansion. So at the expansion process, this path will happen. Then after reaching this exhaust valve opens, if you open this exhaust valve at this point, you can have again a cyclic process, and we can have exhaust. Then again we can have intake like this. So again we can have the initial point, then there will be a cyclic process. So this process will be a routine one for all the IC engines. Just try to remember this PV diagram. Right, so initially what we are using the air fuel mixer will be in atmospheric pressure. So at this point there is the pressure will be P atmospheric, right? Then we have the second diagram will give you ideal Otto cycle. So this is actual four-stroke Otto cycle. Then we have ideal Otto cycle. So we can have for theoretical purpose the ideal Otto cycles. So again we have isentropic compression, then constant heat addition, then isentropic expansion, then constant heat ejection. That is for your Carnot cycles. So this is for your PV diagram. So this is a PV diagram of a Carnot cycles that we seen in the earlier slides. Right. So like Carnot cycle, we have the processes of Otto cycles here. So the first process is isentropic compression, and second process is constant volume heat addition. Then third process is the isentropic expansion. Then again fourth process is constant volume heat rejection. So these four processes comes together will give you a Otto cycle. Right, like a Carnot cycle, we can have the Otto cycle. Just try to remember the processes. We have isentropic compression, then we have isentropic expansion, and then we have constant volume heat addition. But in Carnot cycle, there is a constant thermal, isothermal process. Here, the constant volume heat addition. Then we have a constant volume heat rejection. Right. So note on this: constant volume heat addition and constant volume heat rejection. Then isentropic, that is reversible adiabatic compression and reversible adiabatic expansion. So these four processes in order will give you a Otto cycle. So this is a real Otto cycle PV diagram that you know already. So this is compression, power, then exhaust, intake. So this is a real Otto cycle PV diagram. Then this is idealized Otto cycle PV diagram. So we can have ideal Otto cycle PV diagram as like this. So we have isotherm from at point 1 to point 2. We have isotherm. Then again isochoric. Then we have isotherm. Again we have isochoric. It is constant volume process, right? So also we have a TS diagram. So from 1 to 2 we have a isentropic process. Then 2 to 3 we have a constant volume process. Then 3 to 4 we have again isothermal process. Then 4 to 1 we have a constant volume process. So your PV diagram and TS diagram of idealized Otto cycle will be look like this. Then for formulas we can refer this slide. So for isentropic compression we know the formula, that is P1 by V1 is equal to the formula, isentropic compression. Then for constant volume heat addition, you can have this equation, that is Qn heat transfer will be calculated by mass into Cv into change in temperature. Then the same formula, but for the expansion process, and this is for the heat rejection process. So if heat is added to the system, we can have the positive value. Then if heat is rejected from the system, we can have the negative value of the Q. Then we can calculate the efficiency, thermal efficiency of the Otto cycle. You know the formula W net by Qn. So here we have W net as Q net, but Q net also can be calculated by Qin minus Q out. Then you know the input Qin. Finally, we can have the formula as 1 minus Q out by Qin for Otto cycle. Then if you apply the first law of thermodynamics, this for the 2 to 3 third process, that is constant volume process, then we can have the equation as, you know, the first law, that is delta U is equal to Q minus W. So if you apply that, so then we can replace this one, right? So W net can be calculated by W of other values in the process 2 to 3 plus W of both in the process 2 to 3. So here we have a constant volume process. So the constant volume process will be PdV, integration of PdV from 2 to 3. So, but we know the for constant volume process there is no work done. So we can have this W net will be a 0. There is no value for constant. Okay, there is no value for W in constant volume process. So we don't have the W net here. So we can neglect this. Then finally we can have Q net is equal to delta U. Then thus for the constant specific heat, that is for second process and third process, we can have the equation as like this. So that is, so Q net is equal to delta U. So you know Q net is equal to Q in, that is heat supply to the system. Then that can be calculated by your formula mCv into change in temperature. Right. So if you apply the first law to the process 4 to 1, again there is a constant volume process. Again the formula will be same. Q net will be equal to delta U. Then we can have the same equation, but refer the change in temperature will be in the states. Then we can calculate the thermal efficiency. So you know the formula 1 minus Q out by Qin. So here we have calculated. So Qin will be mCv T3 minus T2, and Q out will be mCv T4 minus T1. So this is your thermal efficiency of your Otto cycle. So just try to recall the formula. Then this can be written. So this mCv and mCv is constant in both the term, numerator and denominator. So we can cancel that. Then finally we can have the equation as like this. Then we can take the temperature 1 and temperature 2 outside. Then we can have the if you take a T1 outside, we can have a T4 by T1 minus 1. If you take T2 in the bottom, we can have a T2 outside. Then we can have a T3 by T2 minus 1 as a final equation. Right. So this is the thermal efficiency of Otto cycle. Then you know the process 1 to 2 and 3 to 4, we have the isentropic process, and this isentropic equation can be written as like this. So T2 by T1 can be written as V1 by V2. So actually there will be a V1 by V2 power n is equal to T2 by T1 power n by n minus 1 equation, but you have to replace the equation like this. So we can, if we cancel, then we can get this equation. So T1 by, because we are having T1 by T2 here, so we have to replace that. So if we replace that T1 by T2, then we can replace V1 by V2 power k minus 1. So here we are using only air, so we can have n as k, that is 1.4. Then for yes, here we are using T3 and T4, so we can have the equation like same. Right, since V3 is equal to V1, sorry, V3 is equal to V2 and V4 is equal to V1, we can have this equation. So we can refer this from PV diagram. From PV diagram, yeah, here there is V. So V1 is equal to V4 and your V2 will be V3. So we can have this equation, and we can write this equation as T4 by T1 is equal to T3 by T2. So finally we can have the thermal efficiency of Otto cycle will be 1 minus T1 by T2. So we can cancel these terms because these are same. Then we have T1 minus T2, T1 by T2. So we can replace this. So T1 by T2 can be written as V2 by V1 power k minus 1. Then the R can be written as V2 by V1, that is your TDC by VDC, that can be written as R. So also we can rewrite the equation as 1 by R power k minus 1. Then this can be used in this equation. We can replace the equation, and finally we can have the thermal efficiency of Otto cycle as 1 minus 1 by R power k minus 1. So this is the final formula for the calculation of the thermal efficiency of Otto cycle. Just try to remember this one. Then this is the comparison of thermal efficiency of Otto cycle with compression ratio. So there will be a direct proportion with these two. So if you compare this, if thermal efficiency is increased, you can if compression ratio gets increased, we can get the increased thermal efficiency. So this range from 6.5 to 10, we can have the typical compression ratio for gasoline engines. So in our automobiles, there will be a compression ratio in this range from 6.5 to 10. If that will be the range, we can get the efficiency approximately 60%. So in our normal automobile, we will use this compression ratio to get this efficiency. There will be up to 60%. You know very well, there is no 100% of efficiency available according to the second law of thermodynamics. So we are using the compression ratio from the range of 6.5 to 10 to achieve the 60 to 70% of efficiency in our automobiles. Then these are for the other working mediums. So normally we have this K will be for ideal gas. Then if you reduce this K, we can, for polytropic process, we can have the again same. So if you increase the K, we can get the increased efficiency. So this will give you the effect of compression ratio on Otto cycle efficiency for other working mediums. Then we can we have formula. Then we can try to solve this formula for Otto cycles. Just to have a look up for this problem. An Otto cycle having a compression ratio of 9.9:1 uses air as the working fluid. Initially, P1 is 95 kilopascal, T1 is 17 kilopascal, P1 is 3.8 liters. So we have to convert. The volume is given in liters. Right. During the heat addition process, 7.5 kilojoule of a heat are added. So Q is given. 7.5 kilojoule. Determine all the temperatures and pressures, then thermal efficiency, then the back work ratio, and the mean effective pressure. So we know the formulas. So we know we have the formula for mean effective pressure. Then we have other formulas to calculate the temperatures and pressures in all the four processes. So we have P1, T1 and V1 values, and we have a Q values here, Q in value here. So we can easily calculate. So your PV diagram will be look like this. So from process 1 to 2, isothermal process, then constant volume heat addition, then 3 to 4 isothermal process, then 4 to 1 again constant volume heat rejection. So T1 given, also compression ratio given, that is R is given as 9:1. So that is V1 by V2 equal to 9 by 1. So we can have R is equal to 9. Right, they gave Q in, that is from process 2 to 3 at 7.5 kilojoule. Then they gave P1, T1, then V1 in liters, that is 3.8 liters. So that can be used for the separate processes. So we can have the first process, that is process from state 1 to 2, isentropic compression. So we have the equation as like this. So T2 by T1 is equal to V1 by V2 over K minus 1. Then the known values. So all the other values can be known. So we have V1 by V2 as 9, and we know air is working medium here. So the K value will be 1.4. Yeah. So air is working medium. So K value will be 1.4. Right. So we know the value for T1. Then we know the value for V1 by V2. Then we know the value for K. And if you substitute, we can calculate the value for T2. That will be 698.4 Kelvin. Just recheck your values with the use of a calculator. Then only we can get the practice. Just recheck the values. So you will get 698.4 Kelvin. Then again we have P2 by P1 is equal to, in the form of these values, the comparison between temperature and volume. Here we can compare the pressure and volume. So if you compare, P2 by P1 will be equal to V1 by V2 power K. So we have the values, other values. So we have V1 value, we have V1 by V2 value, we have K value. So if you substitute, we can get the P2 value. Then if you go to the second process, we have a constant volume heat addition. So in that we have from state 2 to 3. So you know the equation, that is delta U equal to Q net here. So here only Q in will be there. So we have this equation, that is Q2 to 3 equal to MCV T3 minus T2. So also we know this equation, Tv equal to RT. So here we have P1, then we have RT1, and we know the value for R. Then if you substitute, then we can calculate the value for small d1, that is your specific volume at state 1 can be calculated. Then we can have this value as 0.875 meter cube per kg. then uh, then we can have the equation, that is your specific heat addition will be your capital Q by small m, that is this can be replaced as, so from this your small d equal to capital B divided by small m. From this equation we can rewrite the equation as m is equal to, so we can bring this m here, then we can have the equation as capital B equal to small, right? So that was replaced here. Next, capital B divided by small. Okay, we can have it. So this will come here, and this D will come here. So finally we can have small m equal to capital B by small d. So that was replaced here. So m is in denominator. So we have to write capital B by small b. Then this will come inside, and this will be here above. So the final equation of small q will be capital Q into V1 by capital B. So we have the value of V1. It was computed here, and we have the volume that was given in your given data. So we can use that. Then we gave the Q value for the second process. Then if you substitute, we can get this small q value. So that can be used for the process 2 to 3. So this formula can be used. This was small q equal to Cv into T3 minus T2. So you know small q value, and you know the Cv value, and you know the T2 value, and if you substitute, you can calculate the value for T3. Just check the values by the use of the calculators. So your T3 value will be 3103 Kelvin. Then from this you can have another equation, that is your P3 by T3 is equal to P2 by T2. Yeah, V3 is equal, because V3 is equal to P2. Then if you substitute, the P3 value, and we calculated in the previous slide, that is T2 value. Then we know the P3 value. So if you substitute, we can get the P3 value. If you substitute in the formula, we can get the P3 value. So the formula will be repeat for all the 4 processes. So first and third process will be same. Then second and fourth process will be same. So the formula will be same for the processes, and you have to remember the states of the concerned process. Just remember, you have to keep the states in mind. So here we are calculating for the state 2 to 3. So we get the states at 3. Then we can move the process 3 to 4. That is the isentropic process. This isentropic expansion happened here. So again, we have the same equation. But here we have to write 3 to 4. That is your T4 by T3 will be equal to your V3 by V4 power k minus 1. Then the value for T3, and the value for V3 by V4, that is equal to V1 by V2, so that is 1 by 9. Then if you substitute, you can get the value for T4. If you substitute, we can get the value for T4. Then again, we can have another formula, is in the form of pressure and volume. Then if you substitute the known values, you can get the unknown value P4 as 422 kilopascal. Okay. Then again, we have to go to the next process at stage 4 to 1. That is constant volume heat rejection. Again, we have the same Q formula. That is capital Q is equal to M into Cv T4 minus T1 here. So if you we can again this M will comes here. So replace capital Q into small q. So we can have a small q is equal to Cv T4 minus T1. Then we know the value for Cv and we know the value for T1 and we know the value for T4. And if you substitute, we can get the value for small q 4 to 1. Small q 4 to 1 will be 7174. So here heat rejection, right? So this will be minus, right? So the q here will be your minus, right? So then we can calculate the W net, heat supplied minus heat rejected. So we know the heat supply value from process 2 to 3. Then we know the heat rejected value from 4 to 1. So we can substitute to calculate the W net value. To calculate the W net value. So if you calculate, we can get the value 1009.5 approximately kilojoule per kg. Just also remember the units for all the calculations. So we have to complete your problems with the units. Then only you can get the full marks. So just follow the units. So there is around 10 to 9 to 10 units alone. So just try to remember that. So for W, it is Voltan. We have the unit kilojoule per kg. So here we have a W net as 1000 kilojoule per kg. Then from that we can calculate the thermal efficiency. You know the formula, that is thermal efficiency of Otto cycle equal to W net divided by Q in. Right. So we know the W net value here we can calculate, and we know the Q in value from process 2 to 3. We can take that. Then if you substitute, we can get the thermal efficiency of this Otto cycle is approximately 58.5%. Right. So remember that the thermal efficiency should be less than 100%. You know, from the second law of thermodynamics, there is no possibility of 100% of thermal efficiency. Right. So we can get the thermal efficiency of this Otto cycle as 58.5%. Then what else we have to calculate? The MEP, that is your mean effective pressure. So we have the formula, that is W net by, that is your dV. dV is equal to Vmax minus Vm. So we can also relate the equation in specific values. So W net is small W net by dV. Small Vmax minus V minimum. Then we know the values. Sorry, we have to replace the values. So also we know Vmax is equal to V1 here. So if you compare the derived values, if you compare the calculated values, your V1 will be a minimum value, maximum value, and your V2 will be your minimum value. So we can take the values to substitute here. Then we can take V1 outside. Then we can write the equation as V1 into 1 minus V2 by V1. That we know is V2 by V1 is your R. Right. So here. So V net by V1 into 1 minus R. That can be substituted. The values can be substituted to calculate mean effective pressure. So this is your mean effective pressure. So this value should be less than the all four states, that is P1, P2, P3 and P4. This value will be less. So here 1298 kilopascal. Then we have to calculate your back work, right? So compression ratio or back work. So that can be, so just remember this is the formula. Just remember this formula again, compression ratio alone. So you know the compression ratio of back work can be calculated by W compression by W expansion. So from in the process 2 to 3 and 4 to 1 can be taken to calculate the back work of the cycling. So back work can be calculated by the formula W compression by W expansion. So you know for W compression from process 1 to 2 we have delta U, and we have compression work expansion, that is minus delta U, that is in the process 3 to 4. So if you use the formula, we can get that is delta U will be CV T2 minus T1. Then for delta U for the 3-4 process, we can have CV T3 minus T4. Then we can cancel this CV as a constant. Then we have the values T2 minus T1 divided by T3 minus T4. We know the values for T1, T2, T3 and T4. If you substitute, we can get the back work. We can get the back work as 22.5%. Just remember the formula. The back work can be calculated with the use of this formula. So back work is the ratio between the work done in compression process and the work done in expansion process. So that's it for Otto cycle. So we have Carnot cycle in our automobile to activate the IC engines. So this Carnot cycle is taken as a standard to derive these all the cycles. So in this class we will look at the Otto cycles and the formulas of Otto cycles and a problem with the Otto cycles. So just there is only the formulas, only there is 4 to 5 formulas. Just try to recall and remember the formulas. Then we can easily calculate the formulas. We can calculate the problems like this. So then this is the supplementary problems given to you to solve from your end. Just try to solve these 2 problems. Right, so there is 2 problems. So just try to solve. If you have any queries, you can ask anytime. Just try to solve these problems. So because we are lagging time, we are fasting up. So just to try to follow. Then this is again the comparison between the Otto cycle and Carnot cycle. So you know this is your actual Carnot cycle that we discussed in the previous slides. So this is your Otto cycle, actual Otto cycle. Then so if you compare the TS diagram of these two, so for this is the red line. This is your Carnot cycle TS diagram, and this is your black lines. This is your Otto cycle TS diagram. So this is the comparison. So we can take the Carnot cycle as a standard one to achieve this Otto cycle. So remember that the Carnot cycle is a impossible cycle, but we can take the standard for all the other cycles. Right. So we can stop here. Then we see the diesel cycle. Actually, we have a lot of cycles, that is auto cycles, diesel cycles, Brayton cycles are there. So fuel cycles also there. So we will look at that one by one in the upcoming classes. So we can stop here. If you have any queries, you can ask now, or else you can hang up. Thank you. Have a good day.
Thank you, sir.